Alright, so chapter 30 is all about inductance and self-inductance, so I'll try to provide an introduction to that. Inductance is just it's based on the concept we talked about last week. It's because you have, if there's time-changing magnetic fields around a circuit, you get an induced EMF due to the electric field that's created. This is just a shorthand for writing that effect in a simple way that makes circuit analysis easier. Okay, so it's really focused on circuit analysis. Let's consider a specific circuit, okay, which is a couple loops of wire. So we'll have loop 1, loop 2, maybe two different circuits that are next to each other. There might be batteries and light bulbs and whatever else in these circuits. To make it a little more generic, let's consider these loops that they might have more than one turn. So what I mean by more than one turn is that you have a coil of wire, for example, that where the second turn follows the path in space almost identically to the first turn, and the turns beyond that do the same thing. So you have wires that kind of execute multiple transits through the same path in space. Okay, so just to be clear, this is not a solenoid. That's not what I mean. A solenoid is a type of coil, but when I write down here, I'm considering a coil that lies along the same path and goes multiple trips, like running several times around a racetrack. Okay, and so I'll have coil 1 will have N1 turns, coil 2 will have N2, and they'll each carry a current, okay? I2 and I1. All right. Now, these two will talk to each other, okay? The currents in one loop will generate a magnetic field that will thread through the other, right? So if I imagine I have a current through loop 1 that looks like that, that's going to generate a magnetic field that comes up out of loop 1 and goes over and goes down into loop 2. And if I1's a function of time, this magnetic field that I've drawn in red here will oscillate or change in time. That will induce an electric field over here that will affect loop 2. Okay, and same is true in the opposite, vice versa, yes. If I have a current that's flowing here in loop 2, oops, can't do that. Okay, that's going to generate fields that will come out of loop 2 and go over to loop 1, and so the magnetic field created by one will influence the other. Okay. Now, even if I consider one loop by itself, so if I look at back to my red pen here, loop 1 generates a magnetic field that goes through loop 1. So there's actually a magnetic field generated here, and if that's changing in time, the electric field generated by this changing red field will be everywhere in space, including at the location of coil 1. Okay, so it turns out coil 1 can influence itself through changing its current. All right, and I'll spend a little more time talking about that in class, about the self-inductive effect. Okay, but I want to lay down some formalism and definitions on this video, okay? And to do that, what I want to do is consider, one of these loops and talk about what the EMF is due to time changes of the magnetic flux through the loop. Okay, so this is just writing down Faraday's law. I have a magnetic flux phi 1 through the loop, which is due to magnetic fields generated by coil 1 itself and also by coil 2. All right, so let's consider what that well, let me do this first. Okay, let me just say that there's going to be two contributions. Well, I need to do two things first here, sorry. This expression is true if there's only one turn of coil. Let me fix it, okay, by pointing out that if there's multiple turns, I'm going to have in each turn we'll have this EMF in it, and now I add up the EMF in each turn to get the total EMF across the whole coil. So again, because you execute multiple turns around the racetrack, for each one turn around the racetrack you pick up an EMF d phi 1 dt, where phi 1's the changing flux through that racetrack. Okay, so if I have n transits around the racetrack with a wire that's connected, I'll get n times that in the EMF at the end. Okay, so I can break this up into two pieces. There's going to be a piece of the flux that's due to coil 1 itself, Okay, so coil 1 generates a magnetic field through itself, and that flux will be phi 11. And then coil 2, the external coil, will generate some flux that will thread through coil 1, and that'll be phi 12. Okay, let me just look at this. Say, take phi 12. Okay, now if I wanted to write this down from first principles, I would want to write down the integral of B2, okay, integrated over the surface of loop 1 dot dA. Okay, now I can replace this with B sub r. So let me leave the external integral, and then I'll have a dot dA here. Okay, and so I can replace B2 with another integral, which will go like mu naught I2 over 4 pi. I didn't give myself enough room. Let me move this over, and I'll write the dA in the end. Okay, so the magnetic field B2 can be written as mu naught I2 over 4 pi times the integral of dl2 cross r hat over r squared. Okay, now dot dA. Let me call it, just to be clear, dA1 here, because it's going to be executed over the loop 1. Okay, now so what I do is I find the magnetic field in the region of loop 1 due to loop 2, and then I integrate it over loop 1. Okay, so this is a messy expression. We're not going to evaluate it, but what I can do is point out that there's basically I can pull this current out, and what's left over is really just a mess that turns into a number. Okay, so if I imagine that the coils are fixed in space, they're not moving around, they're just fixed in space, this integral is the same no matter what the current is in the two loops. Okay, it's really just a function of geometry. So we're going to define that thing away. Okay, let me go to the next page here. All right, and so we can just write that the flux through coil 1 due to currents in coil 2 is just some coefficient. Let me just call it alpha for now. Alpha times I2. Okay, and this is that messy integral that we didn't evaluate. But it's a constant. So if the coils are fixed in space, and I'm just changing the current in coil 2, the flux through coil 1 this is just a constant number, and I multiply it by this. Now it's a messy number to find, but I can measure it. I can actually go in and measure the flux given a certain current, and I know the number, and I can use it. Okay. Now we usually define this coefficient in the following way, because the EMF in coil 1 is proportional to the time change. Is proportional to N1 times phi 12. We define this coefficient in this expression. Okay, so alpha is really M12 over N, I suppose. Okay, but we define this geometric coefficient, which in this case is called the mutual inductance, using this expression. Okay, and then you can do an equivalent definition, which is N1 times the flux through coil 1 due to coil 1 itself, is defined as what's called the self-inductance of coil 1 times I through coil 1. Okay, all right. And so you can pull out definitions now for L and M. L is just N1 phi 11 over I1, and M12 is N1 phi 12 over I2. Okay, so this is the self-inductance, and this is the what's called the mutual inductance. Okay, and so using those definitions, I can write the EMF in coil 1 due to, now coil 1 might have batteries and other things in it, capacitors and who knows what. Okay, this EMF I'm writing down is due to the changing magnetic field in the vicinity of coil 1. So it's just that component. But you can write it down as minus L1 di1 dt, okay, minus M12 di2 dt. Okay, so I get an EMF in coil 1 due to changing currents in coil 1 and in coil 2. All right, and this makes it a lot easier to analyze a circuit, a system of circuits. You can, because what you want to know about is voltages and currents in the circuit. You don't want to have to calculate flux, and this kind of hides the flux into these coefficients here. But we know that, again, these coefficients tell you about the geometry of the coil. But once the coil is made, that's not changing, and you can measure L and use it in circuit calculations, which are great fun, of course. All right, so let's stop here on this video. Okay.